This video is how to conduct a one-way analysis of variance, both with and without jump. So we're first going to do this by hand. So in a two-sample or an independent sample t-test for means, we looked at the direct comparison of two sample averages, so x1 bar and x bar 2, to draw inference about the population difference mu1 and mu2. But when we have more than two levels of our categorical predictor, so if we have, say, G groups that we're interested in, we have to ask about the equality of those group means in a different way, and we do that via ANOVA, or an analysis of variance. So consider the salary.jump dataset, which is on the course website, and in that dataset we have the salary, the variable SL, and rank RK of 52 professors among other variables. And the question we want to answer is, do assistant, associate, and full professors earn the same salary on average? So, written another way, do these three professor ranks, assistant, associate, and full, earn the same salary on average? So we want to know, is mu1, mu2, and mu3 as our variables of interest, are they the same? And we can answer this using ANOVA. So the first thing we do whenever we're asking a question about the equality or some values of our parameters of interest, we set up our hypotheses. Our null hypothesis is that mu1 equals mu2 equals mu3 in this case, because there are three groups or three ranks that we are interested in. And so our null hypothesis always contains equality. For this null hypothesis to be false, we just need one of those ranks to be different. And it could be that the full professors earn a different amount, that the associate professors earn a different amount, that the assistant professors earn a different amount, or that all three earn their own unique average amounts. So we just need to write at least one mean is different. Remembering to define our parameters and context. So this is mu1, mu2, and mu3 are the true average salaries of assistant, associate, and full professors, respectively. To test this, because we have those three groups, we could, if we wanted to, do a bunch of t-tests, but we talked about in class that would give us this galloping alpha problem. We would lose control of our type 1 error rate, or the probability we would commit at least one type 1 error would be higher than the 0.05, for example, that we really want. So instead we do this using that one-way ANOVA. So we can answer this question with one test, and this controls that type 1 error rate, because if we do one test, we could only commit that error one time. So this is a one-way ANOVA for means. And again, that one way is because we have one categorical predictor. So each way in ANOVA tells us how many categorical predictors we have. In this case, that's rank. The third step in any hypothesis testing scenario is to state our assumptions, and these are the same exact assumptions that we have for an independent samples t-test when we assume equal variances. So we need a quantitative response. In this case, we're talking about salary, and salary is certainly quantitative. We also need independent random samples. So that means in this case we would have had to randomly sample the associate professor ranks, the assistant professor ranks, and the full professor ranks. And that assistant professors can't overlap with associate professors, and they can't overlap with full professors. And we weren't told explicitly that these were random samples. I'm telling you this is a random sample, and we do have that independence of those three groups, so we've satisfied this assumption. The next assumption is that we have approximately normal populations for all groups. and that's so that we can justify using this F-statistic or F distribution later on. And we haven't been told this. So this is, in this case, a true assumption. We don't know about our population distributions. Now, later on, we could check and see if this is a reasonable assumption after we fit the model. But for now, this is a true assumption. And our final assumption is that we have equal population variances, because ANOVA pools those standard deviations in of our groups to get a good estimate of this one overall variance in the population. So we need equal population standard deviations or equal population variances. So we would check that using S max over S min, and as long as that ratio is less than 2, then we'll have satisfied that. So here we're going to remind ourselves again of what our null hypothesis is. We want to test whether mu1 equals mu2 equals mu3. So that's our null hypothesis. And our question is, do the 3 professor ranks earn the same salary on average? So we've stated our hypotheses, we've named our tests, we've gone through our assumptions and checked them for the most part. Now we have to come to the mechanics. So we write our significance level, and we weren't told what it is, so we're going to use a significance level of alpha equals 0.05, so this is just by default. And we know that we always reject the null hypothesis if our p-value, whatever we get from this test, is less than alpha, which in this case again is 0.05. The rest of the mechanics traditionally has been just find the test statistic and find the p-value for that test statistic. In ANOVA, we have to do a little work to get there. So I've already laid out the very bare bones of an ANOVA table, and we're going to fill this in by hand. You're never going to be expected to do this in the real world. You'll always have software available to you, but it's nice to go through an example and see where these numbers come from to hopefully get the idea of, okay, well, why would we reject, or maybe why would we fail to reject, to see what numbers are driving that decision. So we're going to start in our degrees of freedom column. So this DF, this is degrees of freedom. And our between degrees of freedom, or sometimes this is called model degrees of freedom, and that is saying that when you go and fit your model, or if you believe that the null in the worst case is wrong, how many parameters are you fitting? And so we have 3 different means. We have G group means that we need to estimate, and we're going to lose 1 degree of freedom by comparing them to the grand mean later on when we calculate our sums of squares. So we're always going to have the number of parameters for degrees of freedom between minus 1. So here we're estimating 3 parameters, mu1, mu2, and mu3, and we lose 1 degree of freedom, so that's going to be G minus 1, or 2 in this case. For within degrees of freedom, and sometimes this is called error, because it's about the individuals, how they specifically vary. So for our within or our error degrees of freedom, this is telling us about, you know, after we were to pool our standard deviations, this is about that true error degrees of freedom. This is about that standard error, the variability from sample to sample to sample. This is our estimate of that true population standard deviation. So this is going to be that N minus G. So degrees of freedom for error, this is always the number of observations minus the number of parameters. Always, always, always. And we're going to see this again. And so in our sample, we had N was 52, and we had G is 3, so this is going to be 52 minus 3, or 49. And so for total, degrees of freedom total, it will always be n minus 1. Because we're saying, well, what if we can fit everything with just one mean? What if we treat this as just one sample and we don't care what group the observations came from? Well, and if we had just one sample, we would have that one sample degrees of freedom, or n minus 1. And we can see that this is actually also additive. If we added g minus 1 to n minus g, we would get that n minus 1. So df total is always going to be degrees of freedom between plus degrees of freedom for error, and it will always be n minus 1. And so in this case, that's going to be 52 minus 1, or 51. So this is like that one sample scenario. If we just say, let's everything be the same, let's just estimate one mean for everyone. So those are our degrees of freedom. For sums of squares, this is where we start thinking about where the variance in that analysis of variance of idea comes into play. So with SSB, what we see here is that we want the sum, and that summarizes the difference of the y bar j's minus that grand mean y bar. So if we look at our box plot, we see we've got the assistant, associate, and full professors, and then the salaries summarized here. Right? So I've drawn in approximately what our y bar is, that grand mean, which is 23,798. And so SSB is saying, how different is my mean from group 1? And we're going to take that arrow and square it. And then how different is my mean from group 2? We're going to take that arrow's length and square it. And then how different is my mean from group 3? We're going to take that arrow's length and square it. So my SSB, remember, is my sum of squares between. So my between group differences, or my between group variability, is summarized by looking at how different is each group from that grand mean, or is how different each group mean from the grand mean. So I'm going to have three differences, one for group 1, for group 2, and for group 3, that go into and inform my SSB. Generally speaking, I will have 3 group differences, and because each of them, that sum, if I look at those deviations, the sum of my y bar j minus y bars times nj, if I don't square it, that has to equal 0 mathematically. And so when I only have g groups, I lose 1 degree of freedom. So I will have that g minus 1 degrees of freedom for my between groups summary. So for this is the same reason. Whenever you estimate one parameter, in this case I'm estimating that grand mean, that common y, with my y bar, and that's going to cost me one piece of information. So by using y bar here to center to find my deviations, or if we look back on our previous page, if I see that I'm using this y bar to center my observations around, or center my group means on, to find that between group summary, that's going to cost me 1 degree of freedom for my 3 group, or generally g group, comparison. So we can calculate this. This is going to be 18 times 17,769, so that's the group 1 mean, minus the grand mean, 23,798. And we're going to take that deviation and square it to make sure that it's positive. And if that were a big deviation, it would contribute a lot to my between groups sum of squares. So when we talk about a sum of squares, we're always talking about like a sum of squared something. In this case, it's a sum of squared deviations. How much do my group means deviate from my grand mean? So we'll do that same thing for group 2. Now group 2 has a sample size 14, and we're going to see how much the squared deviation for group 2 is. So that would be 23,176 minus 23,798. squared. So again, if this is a big difference, then group 2 is going to have a big contribution to my between group sum of squares. If it's not a big difference, if group 2 has a mean that's very close to my overall average, then it's not going to contribute much, and I'm not going to have a very big SSB due to group 2. And then I have one more group, group 3, and I'm going to find its contribution, sample of size 20, times its square deviation, 29,659 minus 23,798 squared. And when I add all of that up, I get approximately 134,678,3800 with rounding, noting that my y bars were all rounded to begin with. So I need to do something similar for SSW, but SSW doesn't tell me about how my mean for group 1 is different from that overall mean. It tells me about how the individuals in group 1 differ from that group 1 mean. And then it tells me about how the individuals in group 2 differ from the group 2 mean, and so on and so forth. So if I look at this plot, instead of my between groups, I don't care anymore how group 1 differs from the grand mean and how 2 differs from the grand mean. I care about this width and this width and this width. And because we assume sigma 1 equals sigma 2 equals sigma 3, we can say, well, this sample standard deviation should be pretty close to the sample standard deviation in group 2, which should be pretty close to the sample standard deviation in group 3. That's why we use S max over S min is less than 2 to check our assumption. So if we have this kind of relationship, if we can assume sigma 1 equals sigma 2 equals sigma 3, then we can say, well, we're trying to estimate that common standard deviation of population. Let's take these individual sample standard deviations and throw them all together. Let's pool them all together into one good estimate of that sigma. So we pool S1, S2, and S3 into one S sub p, or pooled estimate of sigma, that common standard deviation of the population. And so we start doing that by figuring out what that total, or excuse me, what that within group sums of squares is. How are all the observations that are in this group different from that group mean? And they should all, the difference should all be the same for that group, group 2, and group 3, or within reason. So this SSW, this form here, this sum of the nj minus 1 times sj squared, this is exactly what we did when we pooled our sample standard deviations before. We're just not taking the square root and dividing by n1 plus n2 minus 2 yet. So this nj minus 1 sj squared, for group 1, we'll have n1 minus 1 times s1 squared. So we'll have 18 minus 1 times 2233 squared. And then we need to figure out what sample 2's contribution to this pooled standard deviation will be. So that would be n2 minus 1 times s2 squared. So that would be 14 minus 1 times 1838 squared. And then we do the same thing for group 3. So that would be 20 minus 1 times s3 squared, or 41 squared. And when we work this out, we get 438,946,058. And finally, our total sums of squares, well, we could just figure out the total variability in our sample regardless of which group those observations came from. So this would be like finding just our sample standard deviation. So we would take each individual observation minus the grand mean square it and do that for each observation, add all of that up, and that would give us our SS total, which is what's written here. But SS total really is our total sums of squares, so we can just take our SSB plus our SSW. And that would give us a 1,785,729,858. So we have a huge sums of squares total, but we don't ever really analyze that. We just need that so that we know what our total variability is. So again, think about this analysis of variance. What we have actually done is taken that total variability, if we had just one sample, if we didn't have multiple groups, and we've broken it down to what's going on within each group and what's going on between each groups. So if we consider that total variability regardless or disregarding the groups, we can say, well, then if we do consider the groups, we can say, well, we've got this error or this within groups variability that can't be explained by having different means, but then we still have this other variability that can be explained by having different means, and that's our between group variability, and that's this 1, 3, 4, 6, 7, 8, 3, 8, 0, 0, this giant between group variability. So let's consider that mean squares. So we have mean squared within, for example. That would be the sum of the nj minus 1 times sj squareds divided by n minus g. And so that would be, for example, in this case, n1 minus 1 s1 squared plus n2 minus 1 s2 squared plus n3 minus 1 s3 squared all over, we could rewrite this n minus g as n1 plus n2 plus n3, because this is n, minus 3, because g equals 3. Now we've seen this before. This is a pooled sample variance. So a mean square, this is a variance. So we're finally getting to the variance components of the analysis of variance. We need the degrees of freedom and we need the sums of squares to calculate a variance. So a mean square is always the sums of squares of a specific row divided by the degrees of freedom for that row. So in this way we can get mean squares for between groups to get a variance about between groups, and we can get mean squares within to get variability within groups, and that's what's going to get us to our test statistic. So mean squares is always sums of squares divided by degrees of freedom, and so this is our variance. So if we want mean squared within, or excuse me, mean squared between, we're going to just do SSB, or SS between, divided by degrees of freedom between. And so that's going to be 1, 3, 4, 6, 7, 8, 3, 8, 0, 0, divided by degrees of freedom between. Well, remember that was g minus 1, so that's divided by 2. And that's going to give us an MSB of 673,391,900. So this is a huge, seemingly MSB. This is our between groups variance. And we want to know, is this big relative to our within groups variance? So we're going to calculate MSW. MSW being a mean square, we need to get our sums of squares W now, divided by our degrees of freedom W. And that's going to be 438,946,058 divided by degrees of freedom W, and this again was n minus g, or 52 minus 3, which was 49. So that gives us our degrees of freedom W, or excuse me, our mean squared W of, within rounding, 8958082. So by virtue of having more information or more degrees of freedom for W, we have really shrunk down our variance relative to our mean squares between. So just by eyeballing, mean squares between is much smaller, is much bigger than mean squared W. And this is good if you want to reject. We want a big distinction between our groups relative to within our groups. If we look at our plot again, we see that our groups don't overlap very much. That means it's going to be pretty easy to reject the null hypothesis, and that's because the distinction between our groups and the grand mean is bigger than the distinction, or bigger than the variability that's within the groups. The groups themselves have a small or relatively small variability relative to how different the group means themselves are. And that's the basis of our test statistic. So let's take these values and fill in our ANOVA table some more. So our MSW was 8958082, and our MSB was 673391900. So now we have everything we need to finally get our test statistic, because all of this mechanics has been to get to that test statistic, our F-obs and our p-value. We need to know how big is our mean square between relative to our mean square within, and that is our F-obs. So F-obs is MSB divided by MSW. Always, always, always. So just like our mean squared is always sums of squares divided by degrees of freedom, F-obs will always be a mean squared model divided by sum error mean squared. So what we can do then is go back to our ANOVA table and divide this 673 million by 8.9 million. And that gives us 75.171. So those are the only values we need. This is our F-obs. This is our F-statistic, or our test statistic. So all of that work just to get to our test statistic. Now, it shouldn't take this long on a test. For one, you're not going to be doing all this by hand, and practically speaking, you're not going to be doing your data analysis by hand. You'll have jump, which we'll see in a moment, but this is where things relate. You want a big between groups degrees of variability and a small within groups variability, at least relative to each other. Big and small are meaningless until you compare them, until you calculate that ratio. So you want this F to be much bigger than 1 if you're trying to reject the null hypothesis. So finally we find our p-value. Because we want an F statistic that is big, we want a p-value that's going to look for big F's. So we want an F with nu 1 and nu 2 degrees of freedom that is bigger than our F-obs. Well, what are nu 1 and nu 2? Well, nu 1, this is just degrees of freedom between, and nu 2 is degrees of freedom within. Sometimes these are referred to as the numerator and the denominator degrees of freedom. And that's because the F, remember, was between over within. So if you remember between over within, then you know that the between is your numerator and within is your denominator, so you'll know which degrees of freedom go first and second. So we would find this either by using the jump distribution calculator or going to the F table. So we'll do this using the jump distribution calculator because we haven't looked at that in a while. So here we have the jump distribution calculator and we have the F distribution. Our numerator degrees of freedom is our between groups degrees of freedom. In this case, we had G minus 1 or 3 minus 1 or 2 degrees of freedom in the numerator. Our within groups degrees of freedom was N minus G or 52 minus 3, which gave us 49 degrees of freedom within our groups. And we do not ever have a non-centrality parameter in this class, so we just leave that at 0. And we want to find the probability that we get an F greater than, so we come down here and pick greater than our F obs. Our F obs in this case was 75.171. So our p-value is less than 0.0001. So you can see that our scale here goes from 0 to 7, so we are off the chart, we are actually off the screen. So the probability that we get an F statistic bigger than our current one is infinitesimally small. So we have a tiny, tiny p-value. And so we'll come back and we'll put that in our worksheet, in our ANOVA table. So our p-value, this is the probability that we're greater than our F statistic. The best we can do is say that it is less than 0.0001. But that's good enough information for most people. So now we have our ANOVA table, we've filled it in, we have our test statistic, we found the p-value of our test statistic. Now we can go ahead and write our conclusion. Because our p-value is less than 0.0001, it is less than alpha of 0.05, so we reject the null hypothesis. So here we have our decision, reject the null hypothesis, and we have our justification because we have a p-value that is less than alpha. So now we need to go and put it in context. There is sufficient evidence to indicate that faculty members of different ranks do not all earn the same average salary. At least one rank earns a different amount on average. And this may be unsatisfying because we can't say that full professors earn more, that assistant professors earn less, or that they all earn a different amount. All we can say is that at least one rank is different than the others. We don't know which rank and we don't know how it's different. We just know that at least one rank is different. But there's our context, our decision, and our justification. So how would we conduct this test using JUMP? So we have our salary.jump data set. So we would open that data set in JUMP itself. So these are the salary data, and we can see that we have a variety of other variables besides salary and rank, but salary, SL, and rank, RK, are the two variables that we are interested in this particular analysis. And again, we want to know, do professors of different ranks earn a different average salary on average, right? And the only thing JUMP will do for us is that portion of mechanics. We still have to state our hypotheses, name our test, state our assumptions, do the first half of mechanics where we identify our significance level and rejection rule on our own. And then once we get that ANOVA table from JUMP, we still have to draw the conclusions. So all JUMP does is the number crunching for us. So we would still write the HTA just the way we started before when we did by hand. We would identify our significance level 0.05. We would identify that we're going to reject the null hypothesis if we get a p-value of less than alpha. And we would come here and say, well, what is our F test statistic and what is our p-value? And we can do that using the Analyze menu. So you go to Analyze and you'd select Fit Model. So what we want to do is say, well, our response is SL, salary, so that is our response or our Y variable. Our predictor, our explanatory variable, RK, goes in our model effects box down here. So we would add that to this big box. And that's all we do. So our response goes in the Y variable. Any predictor comes down here in the model effects box. And then we hit run. We get a lot of output, so we're not going to look at the graphs right now. What we're interested in is this analysis of variance table. And we see, once I hide all these things, we see that this analysis of variance table is exactly the same within some rounding differences of the one that we calculated by hand. So we have our source. So remember, between is often referred to as the model. We have within, which is often returned to as error, and we've got C dot total, which is the corrected total. So we've got those three sources of variability: our model or between groups, our within or error, and total. Our degrees of freedom line up, so JUMP has calculated degrees of freedom the same way we did. It used G-1, N-G, and N-1. And then it calculated the sums of squares. So we have, again, within rounding, the exact same sums of squares values that we would have calculated when we'd done them by hand. Mean squares, if you were to look at this, they get mean squares equal to sums of squares divided by the degrees of freedom. And this F ratio is the ratio of between mean squares to within or error mean squares. So this is truly a ratio. It's a ratio of variances, between group variances to within group variances. So if we do this MSB divided by MSE, we get 75, and that's that same F ratio that we found before. And the probability that we get something greater than our F statistic, well, this is the same p-value that we had. So that's how you would do ANOVA by hand, or a one-way ANOVA by hand, and you can also do it by JUMP. So once you get to this point, you can then write your conclusion. Because we have a p-value less than alpha of 0.05, we reject the null hypothesis that all group means are equal, or we can say there's sufficient evidence to indicate that at least one rank of faculty earns a different salary on average.